In this video, I'm going to use Feynman's method to evaluate three single integrals. The idea is to introduce a new variable and then use partial derivatives to evaluate a single integral, which may or may not be solvable by classical methods that you learn in your calculus class. So let's start with a warm-up here. We have an integral from 0 to infinity of x to the fifth e to the negative x dx. Now, we could use integration by parts for this, but I'm going to use Feynman's method. Integral from 0 to infinity. I'm going to rewrite the integrand as the partial derivative with respect to a new variable, call it k. Now, I'm going to differentiate the exponential function e to the minus kx. And I'm going to set k equal to 1 because what we have here is e to the negative x, so k equals 1 and then dx. In order to get this x to the fifth here, I have to differentiate this exponential function 5 times with respect to k. And by the chain rule, that's going to yield 5 factors of negative x. So negative x to the power of 5 is going to be negative x to the fifth. So I'm going to put a minus sign as well, since this is positive, and this is going to be the fifth derivative. Now I can, I'm going to bring out the minus sign in front, as well as the derivative operator, and this is going to be negative fifth derivative with respect to k, and then integral from 0 to infinity, e to the negative kx dx, and this is evaluated at k equals 1. Now, on the outside, the derivative is a total derivative rather than a partial derivative because this integration wipes out the x variable. So what's in parentheses here will only involve k. So inside the integral, the derivative is partial, but outside it's total. So this integral that we have here in parentheses is much easier to solve. So this is going to be a negative fifth derivative. And this is, evaluating the integral, this is negative 1 over k e to the minus kx. And then evaluated from 0 to infinity, evaluate at k equals 1. And so if I plug in infinity here, this is going to be 0. And then plugging in 0, that's just 1. So this is negative fifth derivative. And this is going to be 1 over k, evaluated at k equals 1. All right, and if I just rewrite this, this is going to be k to the negative 1. And now I just use the power rule. I differentiate it 5 times, so this is going to be, let's see, negative 1, negative 2, negative 3, negative 4, negative 5, and this is going to be k to the negative 6. So yeah, 5 factorial, that is going to be 120, and there are 6 negative signs, so that's positive, so 120 over k to the 6th power. Oh, and this is evaluated at k equals 1, can't forget that. And if I just plug in, so now that the differentiation is done, now I plug in k equals 1. And when I do that, I get 120. Now again, this is, I could have gotten the same result by using integration by parts. So Feynman's method here is an alternative way to solve this integral. All right, let's move on to a more complicated integral. This here is going to be the integral from 0 to 1, and then x squared minus 1 over ln x dx. Now, the way we approach this one, this is also not solvable by standard methods from your calculus class. So this should be interesting, I think. So yeah, the way we approach this is by introducing the function f of t. This is going to be integral from 0 to 1, x to the power of t minus 1 over ln x dx. So the goal here So I'm going to use a different color here to, so the goal is to find f of 2 because we want this integral here. So yeah, so I'm going to differentiate this function now. So f prime of t, this is going to be d dt of this integral. Oh, whoops, not on the exponent. That's going to be minus 1 over ln x dx. And these limits of integration are constant, so I can just bring the derivative inside, changing it to a partial derivative. So this is integral of 0 to 1, and then partial derivative of t of this fraction here. And I'm going to rewrite this as x to the t over ln x minus 1 over ln x. And the reason I'm doing this is because to show you that this term here does not involve t, so the derivative of this with respect to t is going to be 0, and so I just have one term here in the integrand. So integral from 0 to 1, and then 1 over ln x. Ln x is a constant, and it can be pulled out in front of the derivative. So derivative with respect to x to the t, x to the power of t dx. Now, to evaluate this derivative, t is in the exponent, so we can't just use the power rule. That would be a mistake. So we have to rewrite this as an exponential function in terms of the exponential function e. So integral from 0 to 1, 1 over ln x, and then partial with respect to t. This is going to be e to the power of ln x to the t. And now I'm going to use the property of logs that says I can bring down the exponent in front. So I'm going to rewrite I'm going to put the t right over here. Yeah, so the derivative of the exponential function, this is going to be 1 over ln x, and then so it's going to be the same, e to the t ln x, and then multiply by the derivative of the exponent with respect to t, and that is just ln x dx. And as a result, this ln x cancels with the one on the bottom. And so our integral has simplified considerably. This is going to be integral from 0 to 1, and then so e to the t ln x. I'm going to rewrite this so I can bring the t back up here and say that this is the integral of x to the power of t dx. And this I can evaluate very simply. This is going to be x to the power of t plus 1 over t plus 1, and evaluated from 0 to 1. Plugging in 0 for x yields 0, and plugging in 1 for x yields 1, because 1 to any power is just 1. So f prime of t, this is 1 over t plus 1. Now, as I said before, the goal is to find f of 2. We know what f prime of t is, and so we can find f of t by integrating. So f of t is going to be the integral of 1 over t plus 1. That is just a natural log of t plus 1 plus some arbitrary constant. Now, the way we determine this arbitrary constant is by looking back at the original function here. What value of t can I plug in here that I can know what this function is? And the answer is if I plug in t equals 0, the numerator here is going to be 0. So f of 0 equals integral from 0 to 1, 0 over ln x dx. This is going to be 0. So I can use this condition to evaluate the constant of integration. So f of 0 equals ln of 1 plus c. This is equal to 0, and that means that c equals 0. So f of t equals just ln t plus 1, and that means that f of 2 is ln 3. And this means that our original integral is equal to ln3. That's how we use Feynman's method to evaluate this integral here. All right, so let's do one more example. This one here is also unsolvable by standard methods. So we have here the integral from negative infinity to infinity of sine x over x dx. And yeah, so the first thing is, the first thing I'm going to do is recognize that this integrand is an even function. If I plug in negative x for x, the integrand will not change. And because it's even, I can rewrite this as I can say that this is double the integral from 0 to infinity of sine x over x dx. And now I can, so as before, I'm going to define a new function g of t, and where t is going to be some new variable here. So this is going to be integral from 0 to infinity sine x over x times e to the minus tx dx. So let's see. Our goal is to find a g of, let's see, that's going to be 0. And once I know what that is, I can just plug that in here, and it'll be 2 times whatever g of 0 is. All right, so as before, I'm going to take a derivative of g of t. So g prime of t. Let's see, this is a derivative of this integral here, sine x over x e to the minus tx dx. And when I bring in the derivative inside the integral, it becomes a partial derivative. So partial derivative of the integrand. Oh, I'm sorry, this is it's with respect to t. So this is sine x over x e to the minus tx dx. And x is treated as a constant here, so I can bring it out in front of the derivative. So this is integral from 0 to infinity sine x over x. Now the derivative of the exponential function is going to be the exponential function. And then I multiply by the derivative of what's in the exponent with respect to t. That's negative x dx. And the x's cancel out, and I'm just left with, let's see, negative integral from 0 to infinity. Let's see, this is going to be e to the negative tx times sine of x dx. Now, I could use integration by parts for this, but that's too tedious. So I'm going to rewrite the sine function in terms of exponential functions. That will make it easier to evaluate. So negative integral from 0 to infinity, e to the minus tx, and then we have here e to the I to the x minus e to the minus I to the x over 2I dx. Now, 2I is a constant, so I can bring it out in front. And if I distribute the minus sign to get rid of that, it's going to be 1 over 2I, and then integral 0 to infinity, e to the minus tx times e to the minus ix minus e to the ix dx. And now I'm going to distribute the exponential function, and this is 1 over 2I. Okay, so this first integral here is going to be integral from 0 to infinity, e to the minus t plus I to the times x, and then dx. and then minus integral from 0 to infinity, and then e to the, what is this, negative t plus I times x dx. All right, and now these are just exponential functions. I can integrate those very easily. This is going to be 1 over 2 to the 2 times I, and then let's see, this first one here is going to be negative 1 over negative t minus I, and then e to the negative t plus I times x from 0 to infinity, and then minus 1 over negative t plus I times e to the negative t plus I x from 0 to infinity. All right, and just plugging in infinity, these terms go to 0, so what's left is going to be the result plugged in at x equals 0. So this is 1 over 2I, and then 1 over, it's going to be the negative because 0 is in the lower limit, so plus I, and then same story here, it's going to be plus 1 over negative t plus I. And if I just add these fractions here, the t's, so this here is going to be 1 over 2I. And then, so I have, so in the numerator, I have negative t plus I plus t plus I. The t's cancel out, and I'm left with 2I on top. And if I multiply the denominators here, that's going to be negative t squared, and then I times I, that's negative 1. The 2i's cancel out, and this is negative 1 over t squared plus 1. And again, this is equal to g prime of t. So now that I know what g prime of t is, the goal is to find g of 0, and I can find g of t by integrating this. So g of t, the integral of 1 over t squared plus 1, that's inverse tangent. So negative inverse tangent of t, and then plus some constant of integration c. Now again, the way we figure out what c is, we have to look at the original function here and figure out what value of t do I know this function. And the answer is, if I let t become very big, if I let t go to infinity, this g of t is going to be 0, because the exponential function completely makes the integrand go to 0. So limit as t goes to infinity of g of t equals 0 because of this exponential function. It completely wipes out, or it makes the integral go to 0. So this here is my condition to figure out what the constant of integration is. So limit as t goes to infinity of g of t. Now, so the inverse tangent function, the graph of that looks like this. So so y(t), this is y equals inverse tangent t, and the y value is positive pi over 2, negative pi over 2 on the bottom. So so as t goes to infinity, the inverse tangent approaches pi over 2. So this is negative pi over 2 plus c. This is equal to 0. That is my the condition, this one right here. And so I can solve for c. That means that c equals pi over 2. And so g of t is pi over 2 minus inverse tangent of t. And so g of 0 equals pi over 2. The inverse tangent of t is going to be 0 here. And that means the original integral here is going to be 2 times pi over 2. That's just pi.